You are audible.
Okay. Good evening, all of you. We are going to begin the inaugural session of the one-day national webinar to celebrate National Science Day, organized by the Department of Physics in collaboration with IQAC, Victoria Institution College. National Science Day is celebrated in India on 28 February each year to mark the discovery of the Raman effect by Indian physicist Sir C.V. Raman on 28 February 1928. The topic of discussion is relativistic quantum physics, textbook to technology. It is a very interesting and effective not only for the students and research workers of basic sciences, but also useful for the development of knowledge towards technological advancement. On behalf of the Department of Physics, Victoria Institution College, Kolkata, I express gratitude to Dr. Kumara Srinivasan, teacher in charge, Victoria Institution College, for consenting to be patron of this national webinar. We are very much grateful to the eminent speaker, Dr. Sudipto Kanungo, Assistant Professor, School of Physical Sciences, Indian Institute of Technology, Goa, for his consent from his busy schedule. We also express my gratitude to Dr. Patrolekha Mukhopadhyay, Coordinator, IQAC, and Associate Professor, Department of Zoology, Victoria Institution College. In this context, I request Dr. Srinivasan, teacher in charge of our college and chief patron of this webinar, to deliver the welcome address. Ma'am.
Thank you, Shivindu. First of all, a very good evening to all of you present here. And on behalf of Victoria Institution College, on behalf of the Internal Quality Assurance Cell of the college, and very importantly, on behalf of the Physics Department, students and teachers alike, I would heartily like to welcome Dr. Sudipto Kanungo of Indian Institute of Technology, Goa, our honored speaker for today. And also, I would like to welcome all who have kindly joined us today on this occasion. This is a very special day in the national life of our country, India, a day on which we proudly remember the great Indian scientist and his very great contribution to the world of science overall. I'm sure webinars such as this will very significantly contribute to the spirit of scientific inquiry among our students who are attending this program. But what is more, I firmly believe that today's session will not only be useful to the enhancement of scientific knowledge, but of our students and everybody, but will be also very helpful in making them, in welcoming them, in inviting them to spread the scientific mindedness among all of us in the society. That is, in a very big way, I think that this will contribute to help weed out much ignorance, superstition, and darkness prevailing even in the 21st century in Indian society. I, as a person who is not a student of science, who never was, however, would at least like to see and understand the Raman effect in our society in this way. That is, the Raman effect, which will be percolated among us all through today's students who will be tomorrow's scientists. Thank you.
Okay, thank you, ma'am. Thank you for your wonderful deliberation about the motive of the celebration of this landscape. So now we are going to start the technical session of this national webinar to celebrate National Science Day. Today's speaker is Dr. Sudipto Kanungo. It is my great pleasure to introduce Dr. Sudipto Kanungo, Assistant Professor, School of Physical Sciences, IIT Goa. His research area is density functional theory-based ab initio electronic structure calculations of quantum materials in the areas of the electronic structures and of correlated oxides, quantum magnetism, topological phases of materials, two-dimensional materials and heterostructures, etc. He did his PhD degree in the year of 2013 on first principles study of noble materials from S.N. Bose National Center of Basic Sciences, Kolkata, India. He did his postdoctoral work from 2013 to 2016 in the Max Planck Institute of Chemical Physics of Solids, Dresden, Germany, and in the Center of Emergent Matter Science, Riken, Wako, Japan. He published a numerous number of research articles and reviews in well-reputed journals of very high impact factor. So now I request Dr. Kanungo to deliver his lecture. Sir.
Yeah. Before starting, just let me share the screen. Is the screen visible?
Yes, it's visible. It's visible. You
Okay.
can,
Yeah,
it's okay.
Okay. So, let me first start by thanking the entire team of the Victoria Institution. Special thanks to Dr. Srinivasan and their nice event they are organizing this in the day of to celebrate the National Science Day. And I would like to also thanks to all the audience who are present here in the late evening 7 p.m. We are starting almost 7:15. So by stating these things, I would like to start what I am going to present today. So when I have been asked to give a kind of presentation or in the occasion of the National Science Day, then I thought that what should be the appropriate topic to basically justify the occasion that in that day I am basically speaking about the topic. So then I found a very interesting thing. So okay, before going so slide is changing, right? Hello.
Yes, slide is changing.
Okay.
Yes,
So
slides are
as
visible, but
okay.
now we can see only the Sudip. Yeah, it's moving.
Is moving, right? Okay. So
Yeah, it's moving. Perfect.
Okay. So as mentioned already, that basically we are celebrating the National Science Day every year because of this Raman discovery of Raman effect by C.V. Raman, not that far from the Victoria Institute, that cultivation of science. So every day, every year, basically, found that the Department of Science and Technology, basically they started this celebration of the National Science Day from designate this day as a National Science Day in around 1986. But after some years, around 2000, every year the Department of Science and Technology announce a theme. Announced every year there is a theme for that particular. Sorry for this. Some call is coming. Okay, so every year the National Science Day, because in the occasion of the National Science Day, the Department of Science and Technology announced the specific theme for that particular year. And I found very interesting theme for this year, that is an integrated approach in science and technology for the sustainable future. I found this theme is very interesting and is relevant. As Professor Srinivasan correctly mentioned, that is not only the celebration of that particular day, it is basically setting up a culture and setting up a mindset. And that mindset should not be concentrated only those who are actively involved in the field of or professionally involved in the field of the science and technology, academics, education. Should propagate throughout the every level of the society. And in that scenario, this integrated approach is very much required. And then I thought, okay, let's talk about something that this integrated, because of this integrated approach, some new discoveries or some new path-breaking thing have been that we can understand, that because of this integrated approach of two apparently disconnected field, or more precisely, if I say not disconnect field, apparently they are basically not connected, but if we integrate these two fields, then we may come up with a completely different paradigm of understanding, and that leads to a future technological development, or the setting up a completely different type of futuristic technological platform. So I took a kind of assuming the most of the audience are basically the students, and those who are expert in the field, they please excuse me, they found a lot of thing is basically boring, but I made this thing to focus on the mostly the students' perspective, that the relativistic quantum physics that we used to study in our textbook curriculum, there is always a mindset that some of the part is there, and we are studying as a fundamental knowledge to understand the fundamental or the basic of the subject. And there is always that basic physics, some are the applied physics, some basic science, some applied science. But if we integrate these two things, that those who are doing the applied kind of business and those who are doing the fundamental kind of business, if we just combine these two things, then probably we can get a completely path-breaking thing, which is not been thought of that one can get. And exactly this thing happened if we when we are trying to understand the few recent discoveries. And one of the discoveries is the now everybody knows, those who are at least in this physics community, that the discovery of graphene. And this discovery of graphene is nothing but an integrated approach of the fundamental and application, or more precisely, if we try to combine the knowledge of the relativistic quantum mechanics, what we used to study in our textbook, And if we combine those who are basically expert in this synthesis of the material, or how to, or in the chemistry chemistry community, then we can come up with a very interesting or path-breaking thing is called graphene. So that's why I thought, okay, let's try to understand this graphene thing, which is a kind of boom, and everybody is looking that probably in the future all the silicon industry can be replaced in the by the graphene, but it is still a futuristic approach or futuristic dream, but there is a finite steps have been made in that direction. So now if we just try to understand that how this integrated approach basically discovered the graphene, and why this graphene, to understand the graphene, this relativistic quantum mechanics is required. So this is the basically outline of my talk that I am trying to present here. So before that, just for the sake of kind of advertisement, that I am basically doing a quantum material modeling at IIT Goa. Basically, my interest is to do the ab initio quantum chemical modeling for the quantum phases of matter, mostly the electronic structures for the oxides, quantum magnetism, topological phases, and the different type of 2D material, including graphene or all the van der Waals materials and heterostructure and magnets. So this is basically my field of research. So yeah, so going back to this, so the outline, I will just briefly tell you that what are the basically pillars of our modern physics that we can understand. And this and basically there is a mostly the modern physics two pillars, that are the relativity and the quantum physics. And now if we combine this thing, and then we can come up with the relativistic quantum mechanics, and this relativistic quantum mechanics can lead to a material realization, and that material realization basically the graphene, and how this integrated approach basically gives us the freedom or gives us the opportunity to use the graphene as a future device, which device, or more precisely the future superior device compared to the existing. So this is the basically picture taken from the Nature Physics, and it basically highlighted the top 10 physics discoveries in last 10 years. So the graphene is one of them, marked here. So in that way, graphene is already a kind of setting up a boom that is a future of all the devices, mostly the electronic devices. Okay, so if we just start with the beginning of the modern physics, that we know that there is a light is an electromagnetic wave, and the nature of this light in terms of the electromagnetic wave is well established through the Maxwell's equation. Then there is a famous experiment had been done by the Michelson and Morley, and this is the one of the famous null experiment, that is they basically try to calculate or try to measure the velocity of light into perpendicular direction, and how the relative velocity can change of velocity of light, but they found that is a outcome is null. So that means basically the velocity of the light doesn't depends on the if we measure in the two perpendicular direction, and that's basically leads to a completely new paradigm or the new subject, which is called the special theory of relativity. And this Einstein framework is a complete mathematical framework to put the relativistic theory on the paper. So that basically, if I completely just summarize all this thing, is nothing but a speed of light is absolutely constant, and this time and the space, now we need to treat them in a equal footing, is also that means all the finite mass object cannot move faster than the light. Light is velocity is the maximum. And very interestingly, the mass and energy are now two are not the completely different entity, they are basically equivalent. And equivalent through the famous Einstein relation, E square equal to P square C square plus M square C to the power 4, or E equal to E equal to E square equal to this. Now, if we just try to represent all this thing in graphically, that basically, if we have my cursor is visible to you, right? So the classically, when my velocity is very less than this velocity of the light, so we are basically non-relativistic regime. Then my energy, if we try to plot the energy versus momentum, then energy is nothing but a p square by 2m. So if we plot the energy versus momentum is a parabola. Now, if we plot the relativistic energy versus momentum, then it's also looks like a parabola, but not at 0 point. So that means at the momentum 0, I have a finite energy. Now, if we go to the extreme relativistic limit, that is the light velocity of the velocity is equal to c, and that can be possible only when the mass is 0. If the mass is 0, then what we will going to get, this is a completely straight line. That means basically if we put m equal to 0 here, then E equal to Pc. So that is completely, if I plot the energy versus momentum, is a completely straight line. So why I'm showing this three plots, that will be clear when after few slides. Okay. So in a classical, the bottom line or take home message is the simple, that when we are in a classical domain, my energy momentum is a parabolic distribution. When we are in an extremely relativistic limit, then my energy momentum is a straight line or linear. Okay. So now then the second pillar of the modern physics is the nothing but a beginning of the quantum physics. So in quantum physics, we know that there is a failure in description of the stability of the atom. So then all because of this experimental evidences coming up around 90s, slightly late 90s, slightly 1910 or something like that, all the quantum physics picture will coming into all the quantum concepts are coming into the picture to explain all the existing or all the observed phenomena. And these are the few, I would say, the few bosses of the quantum physics. That is, because of them, the whole quantum physics is basically developed and contributed in a different way, starting from the wave particle duality, wave function, all the probabilistic interpretation of the quantum physics, uncertainty principle, all the new concepts that is not existing in the classical physics are coming into the picture to explain the newly observed all the phenomena. Or so now the thing is that the most important thing we have basically a coming outcome of the quantum physics is the quantization. This quantization in terms of the energy level. And these energy levels of quantization is basically what is showing the quantization of the energy levels for the hydrogen atom problem and the probabilistic distribution of the wave function, which is basically all the hydrogen atom orbitals. Now, the thing is that these energy levels, all these things, how we can get the evidence of the quantization that indeed the quantization is happening. If we treat the in terms of the quantum physics, is there any evidence in a macroscopic world or in a macroscopic domain? So yes, there is indeed a real life evidence of the quantization or the quantum quantization. This is nothing but a quantum Hall effect, and this quantum Hall effect is the evidence that indeed the quantization is happening, and this Hall effect is nothing but because of the Lorentz force. And this Lorentz force, if we plot the resistance versus magnetic field, and if we just measure the resistance of the if we place the magnetic field along the z direction, and if we apply the current along the y direction, and if we measure the voltage along the x direction, so basically if we measure the cross voltage, that will give you the Hall resistance. Now if we just plot the Hall conductivity, and that will give you a kind plateau. This plateau is basically the integer multiple of the E square over H. H is the Planck constant, E is the electronic charge, and E is the basically your either integer or half integer, or the fraction. So I'm not going into that detail. So, but the main idea is that this quantization of the conductivity or Hall is the example that indeed there is a quantization in a macroscopic world also. Okay, so till now is fine, but there is also some other surprise in the quantum world, that is the quantum spin, which or the spin of the electrons or have no understanding in terms of the classical physics. Is a completely quantum object, is a nothing but a quantized angular momentum. Now in angular momentum is very interesting, because if we just rotate the quantum spin by 360 degrees, then it will pick up a negative sign or property of a quantum spin. So this is basically showing in a cartoon picture, that if we have a kind of Mobius strip kind of thing, and if we roll it, then if we just fix at a particular point, and once it is rotated in a whole 180 degree, then it will be either in one time it will be in a top side, and others after the rotation. It is a representation that if we have a kind of spin, quantum spin, and if we rotate it is a 360 degree, then it will basically pick up a negative sign. This is also a very new thing in a quantum world. And most importantly, this spin is not all coming out from the Schrödinger equation, that is basically the master equation of the quantum mechanics, or you can say the starting equation of the quantum physics, equivalent to the Newton's equation in the classical mechanics. This spin is not a spin will not will come out from the Schrödinger equation automatically. So that is the one problem. So now the thing is that we have one side we have a relativity, another side we have a Schrödinger equation based quantum mechanics. But problem is that if we want to combine these two things, relativity plus quantum physics, we cannot simply combine these two, because we need to satisfy few conditions that the Schrödinger this equation should satisfy the Lorentz invariance as well, to make a frame of reference independent. But one can ask that why we need to combine this relativity and quantum physics. Yes, it is required. Why? One reason is that some of the phenomena we cannot explain within the non-relativistic Schrödinger equation prescription. One of the example is, as I mentioned, in a quantum spin of say for example the spin of the electron. You cannot explain through the Schrödinger equation. However, what we are doing, how we are basically treating, that we are ad hocly putting the spin wave function in the Schrödinger equation, but it is not a automatically outcome of the Schrödinger equation. So similarly, we have also the electron positron pair, or the particle move at the relativistic velocity, we cannot explain or we cannot describe all such thing without relativity and the quantum physics, or unless we combine. And another very important failure, that for the massless particle like a photon, if we want to do a quantum mechanical description, the Schrodinger equation cannot do that. So we have to combine this relativity and quantum physics. So, and because of that, whole relativistic quantum mechanics is basically required. Now the problem is that how we combine these two. The combination to do the merging of these two things, there is a first attempt of combining this relativity and quantum mechanics, or in the formal name is a relativistic quantum mechanics, is done by the Klein and Gordon. And basically they did a very simple task, simple thing. They replaced the energy operator and the momentum operator and put it in this equation, simple equation, and they found this is the simple form of the Klein-Gordon equation. Or if we write down in a covariant format, it will be like this. But there is a problem in the Klein-Gordon attempt. Although this is a there is a attempt, but there is a problem. What is that? The advantage is that, or the success is that, is now if we just replace now this Klein-Gordon equation is low range invariant, is fine. This was not the invariant, so this problem is overcome. Now it's also valid for the zero spin particle, that is also fine, but there is also some problem. What is that problem? Problem is that if we calculate the energy from the Klein-Gordon equation, the energy is basically giving you the negative energy part also. Although there is a physical interpretation of the negative energy, but that time it was not very clear why the negative energy is coming into this thing and how physically we can explain. Also, there is a problem because of this negative energy, your probability amplitude or the probability density become a negative. And what is the physical interpretation of that is there is no explanation. So these are the few drawbacks of the Klein-Gordon equation, or the first attempt to combine the relativity and quantum mechanics. Then the Dirac come into the field and they modified slightly. And how basically they did this thing, how he did this thing? He did a very simple thing. He did basically in the Klein-Gordon field. So if I go back, so basically in the Schrodinger equation, the space part is basically double derivative, whereas the time part is a first order derivative. Space part is a second order derivative, time part is a first order derivative. Klein-Gordon, what they did both time and space is a second order derivative. Now Dirac did that both time and space in a first order derivative. And how basically they write down the equation is that in a very simple way, he wrote this equation of the relativistic Hamiltonian, that I can write down the Hamiltonian that alpha dot p plus beta mc square psi equal to I del psi del t. So p is my momentum, alpha is some constant, beta is some constant, m is the mass. So if we just use this thing, then he interpreted that this alpha is nothing but a 2x2 matrix, and this 2x2 matrix is basically consists of this some sigma, and this sigma is nothing but a Pauli matrices, Pauli spin matrices. So basically the sigma is now is a 4x4 matrices. So here is a 2x2 component, here is a 2x2 component. So as a whole, this is a 4x4 component. And I also designate that give the some anti-commutation relation that need to satisfy by the alpha and beta. So the so what is the outcome of that? outcome is that very interesting. Outcome is that if we do a little bit of algebra of, or in the starting with the Dirac equation, you will get the energy and momentum now linear. Okay, so energy and momentum is now a linear, and also now the wave function is basically 4 component spinor wave function. Now if we just plot the energy versus momentum, it will look like this. So basically the linear dispersion, and the negative part is basically designated as an antiparticle, and the positive energy part as a particle antiparticle. And also there is a called the chirality. I will come to what do you mean by the chirality. So basically the chirality is, you can think of in terms of the helicity, that if we just right hand clockwise and anti-clockwise, if we do the momentum, so then you will pick up a negative sign. So you can think of that the particle moving in a right hand side is basically antiparticle is moving in the left hand side direction. So in this way they interpreted the negative energy. But the most important outcome that we are going to use for at least to understand how this basically leads to the technological discoveries is that energy and momentum is a linear, and the wave function is now the 4 component wave function. These two are the main outcome that basically leads to the discovery of the graphene. Okay, so now the fundamental parts we have discussed. Now if we try to understand how basically these this fundamental understanding, till now we are doing all this mathematics, all these things as a to understand the physical knowledge, all these things, but how we can use this thing to do some technological advancement or some breakthrough in the technological field, that is coming in the materials perspective. So usually the materials perspective, things in the different energy scales is completely very low energy scales, is around milli-electron volt to electron volt. However, what we are doing, the relativistic thing, is very high energy scale. So apparently these two things are very different. The domain energy scales are different, but if we do a integrated approach, that if we use the knowledge of the high energy scale, high energy physics, and use that in a low energy physics, then we can discover many interesting things, and that is basically we will going to discuss or going to show you. And that basically leads to the discovery of the graphene in 2010. So probably all of you are heard the name graphene. Graphene is a basically you can think of that most of the good properties are there. I am not saying all, most of the good properties are there. Is a high mobility, and that will lead to give a huge basically useful for the future electronics. Is a completely transparent, so optically used. Is a topologically robust, so that means basically within some defects, all these things, the property will not going to hamper. Also is a chemically very interesting hybridization is there, and very importantly is a very thin, strong and light. So most of the good properties are there to use it in terms of the device. Now you can say that okay, it's fine, but from where this relativistic thing is coming into the graphene? So yeah, so before going to that, I just give you a very brief introduction about the graphene. What is that? Graphene is nothing but a two-dimensional sheet of the carbon arranged in a hexagonal lattice, and this is basically two penetrating interpenetrating triangular lattice. You can say it is a 2-atom basis system. And if we just try to understand all the good points, is a high electron mobility, is transparent, is almost optically transparent, is very strong, is stronger than the Young modulus is strong, higher than the steel, is very much flexible, and because of all this thing you can use it. I will just skip all this detail. Yeah, so I will just briefly tell you what is the basically crystal structure, because it will require to explain few things. So if it is nothing but a Brillouin zone, this is a hexagonal lattice, and this is Brillouin zone, is a hexagonal Brillouin zone, two-dimensional. Don't go, need not to go all the details of the values and everything. Just overview is that the hexagonal Brillouin zone is the hexagonal, and hexagonal Brillouin zone have three points, three high symmetry points. One is K prime, M, and K, two corner, and one is the center of the one arm. So now if we know this is the hexagonal Brillouin zone, and if it is in terms of the hybridized orbital, it's basically the sp2 hybridization, and in sp2 hybridization there is a sigma bond between these two carbon atoms, and there is a pi bond, which is basically nothing but a carbon pz orbitals is basically standing out of the plane, and this is basically the pz orbital, and all the sigma bonds which are in the plane of the hexagon, they form an sp2 hybridized orbital, and that is basically span throughout the lattice. Okay, so now this is basically gives us a very interesting electronic property. So in terms of the physics or physicist, what is basically we know? That is, we have a conductor where the valence band and conduction band overlap each other. We have an insulator where the valence band and conduction band are well separated with a large energy gap, and we have semiconductor which have some small gap that can be overcome through the activation process. However, if we try to do a simple modeling of the graphene using the tight binding approach, and then tight binding approach is basically the nearest neighbor hopping. If we just consider the nearest neighbor hopping, the tight binding approach, if we do simple textbook calculation, then what I'm going to get is this. The energy, what we will going to do, don't go to the all the detail of the value of energy, just look at just try to concentrate on the graphical representation. So if we will get this energy something like that. Now if we just sorry, if we plot this energy as in terms of the k-axis, so basically k-axis means in terms of this Brillouin zone high symmetry k points, then we'll found the very interesting thing, that we'll find these 6 points where the valence conduction band and valence band touching with each other. Okay, so these 6 equivalent non-inequivalent points in the Brillouin zone, basically 3 and 3, two different types. 3 are in a k point and 3 in k prime point. At this point, 6 points, the valence band and conduction band are touching with each other. And if we just make a zoom of this figure, we will get this. This is basically the band structure of the graphene in very low energy. That means exactly very close to the Fermi energy. And if we just concentrate on the circle, what is marked here, that is basically valence band, the red part, conduction band, the blue part, touching with each other at the corner of the Brillouin zones. And if we just concentrate on the very close to this point, you can see that these bands are basically linear. That means energy and momentum are now energy is basically the linear function of the momentum, and that's why. And here is actually the relativistic things are coming into the play, and these points are called the Dirac points, where the valence and conduction band are touching, and there is a linear dispersion. So this linear dispersion, if we just try to understand from in the case of graphene, is nothing but is a quasi-relativistic phenomena. So that means basically we have a material if we do a simple electronic band structure, and we will found that indeed near the Fermi energy, the bands are basically the linear. That means energy and momentum are now energy is a proportional to the momentum. But this is very unusual. Ideally, we should get a parabolic band. How? Basically, the energy is proportional to the k square. All these normal metals, semiconductor, insulators, all these things, we should get a parabolic band where either it is separated by gap or not gap, but they should be parabola because they should follow the E proportional to k square. But in the case of graphene, we found that here we are basically getting the E proportional to K. That means is a linear dispersion in a low energy scale. So that means the conventional understanding, which is basically existing, is completely different in the case of graphene. And to understand this linear dispersion, we need to bring this the relativistic quantum mechanics understanding into the picture, which explains us that why the bands are linear and what is the resultant of this linearity. To understand this thing, to understand this thing, so since it's a basically linear, and we know that is if we do a relativistic description of quantum mechanics, we will get a linear band. But when we get a linear band, if we put a m equal to a 0 in my in my Dirac equation, I will get the basically energy is proportional to P. So m equal to 0 means basically the massless particle. So that means if we have a electron whose mass is very small, close to 0, then only we will get a relativistic description, and that basically then we will get a linear dispersion. And that is basically explains why in graphene the electron mobility or electron conductivity is so high, because the effective mass of the electron near the Fermi energy is very small, and because of that small effective mass, we can use that to devise or to fabricate the very high speed electronic devices. So here the catch here, so basically the idea is that we in one hand we have a knowledge of the relativistic quantum mechanics in the context of a completely different field, in a completely different context. On the other side, we have a material which shows some unusual property which cannot be explained within a given set of paradigm. But now, if we combine these two apparently disconnected knowledge, and we do a integrated understanding or the integrated framework of understanding, then we can explain and we can design new thing for the future technology that can be used for the upgradation of the future technology. So here actually is a typical example which is using the textbook knowledge, how we can explain a very sophisticated cutting edge discoveries which are basically apparently disconnected. So the story is not ending here. Even we can use when we are discussing the relativistic quantum mechanics, I mentioned there is a two very important point. One is the energy momentum and linear, and another is the 4-component spinor wave function. Now, what is the outcome of the 4-component spinor wave function, or the consequence of the 4-component spinor wave function? What is in the Dirac equation in the case of graphene? How we can utilize this completely mathematical concept in terms of the technological advancement? That is basically leads to a completely new kind of dynamics, which is called the valleytronics. So what is that valleytronics? Valleytronics is nothing but we can use the value of the or the value of in the band structure as one of the degrees of freedom. So we have a basically two different sublattice A and B in the graphene. So we can set a sublattice index isospin, and also we have a two different K points in the Brillouin zone, and that we can designate as a valley index or the pseudospin. One is isospin and the pseudospin. So now if we just combine these two, and then what we will going to get is that we will going to get a four component, basically the wave function. One is for A plus means A sublattice and K for the K point, and another is B sublattice K point, another for the A sublattice and B sublattice for the K prime point. So basically we have one side A and B two sublattices in the real space crystal structure, and we have a K and K prime point in the Brillouin zone. So now if we combine these two, then we can come up with a four component wave function that is basically designated by the two different valley. One is K valley, another is K prime valley. And how they are two different? They are two different in terms of the, you can say, the helicity, or you can say in terms of the pseudospin. So how basically we can write down that, if we write down the energy for the K valley and write the energy for the K prime valley, there is a negative sign where the basically the pseudospin will pick up a complex conjugate. So this whole, and this we can use as a technological. So basically electronic charge we are using to devise the electronic devices, but here we can use the valley index, that is K and K prime, to transfer or to transport the electrons, because they are mutually, they are not scattering with each other, so they can move independently in K and K prime valley. So this is another outcome of the technological kind of frontier, using the four component spinors wave function in from the Dirac equation. So how much time I have?
Another 5 to 10 minutes, okay?
5 minutes. Okay, 5 minutes is fine.
5 minutes, fine. Yeah.
So then, if we just simple use the magnetic field in the graphene, so usually we know that if we place the electron in the magnetic field, there is a Landau levels. In the Landau levels are basically equispace levels in the energy spectrum. For the case of the classical thing. So if we place a relativistic particle in the magnetic field, then what we will going to get, they are not equispaced. Now they are basically proportional to square root of field, you can say. So this is also a kind of you can utilize the graphene for the case to utilize in terms of the quantum Hall effect to fabricate the devices. And also you will get the quantization, and this quantization is basically you can get at the half integer spin, half integer plateaus. So in the case, basically you can get either it is half, 3 half, 5 half, 7 half. So that is basically you can mark as the fractional quantum Hall effect. At the end, I will stop by saying very simple thing, that in the case, if we go back, if I told you that there is a reason that I showed, is that plot? Yeah. So why I'm showing this plot, is at the beginning, in this, when we were discussing the special theory of relativity, that for classical motion parabola, relativistic motion is also parabola, but now at the momentum zero, the energy is not zero. There is a energy, and there is a energy y axis is not at zero, and this is because the mass is there. This mass terms is there, so that is basically the energy equivalent to my rest mass. So that means if we just make m equal to 0, then it goes to the linear. Now that means basically if we use a non-zero mass, then my my energy will not be zero at momentum zero. Okay, so now what we basically got in the graphene, we got the graphene is that a momentum zero, energy zero. Okay, now this is if we just this, if we have a single layer of graphene, then you have a linear dispersion. So momentum zero, energy zero. Now if we make the two layer of graphene, that is one layer, and top of that there is another layer, it is hexagon, same hexagonal layer, then what we are going to get, that your bands are now, instead of the linear, they are starting, that is they now become a parabola, and also they are getting, the gap is opening, and this gap is basically opening because now now basically interaction between the two layers are there, and that is basically equivalent to incorporating the mass term in the relativistic regime. So so that means if we have a single layer of graphene, we have a linear dispersion, is an extreme relativistic limit. That means the electrons are very fastly moving in the hexagonal lattice in two-dimensional plane. Now if we put another layer, so because of this interaction, this the gap is opening, and that's opening, and equivalently you can say there is a effective mass of the graphene electrons are now increasing. And if we just keep on doing this thing, and you can go to the formal graphite structure, which is basically the insulator. Okay, so so that means I can, so in summary, if we just try to do the summary, this thing, in one hand we have a fundamental understanding from the relativistic quantum physics, and another hand we have a kind of materials realization, graphene, all this thing now, which is basically can be used in a technological advancement. But if we unless we combine the knowledge gain from the fundamental understanding, and if we do if we are not doing a integrated collaborative approach, unless we cannot understand the whole picture. So so basically this is a typical example where using the textbook knowledge can lead to the technological discoveries to understand or to explore more universal or the natural phenomena. So with that, I'd like to thanks once again the organizers and the audience for their patience and the opportunity to present or to talk about this this thing in front of the audience. And like to thanks.
Shudipto, there is one question from the audience.
Yes.
Tania Patro, she asked that why we get half integer Hall effects instead of multiple of 1/3 or any other fraction.
Instead of?
And basically what she wants to ask that why in fractional Hall effect, it's only the multiple of half integer, not like 1/3 or any other fraction.
Oh, okay. So that that you can get from this that you can get from this simple formulation, that if you do the Landau level for the relativistic particle, then the basically what is that? So basically you have a n value is here. So now if we put n equal to 0, 1, 2, 3, etc., then instead of then you will start getting all this thing. Okay, so these are the basically the Plato, where you will get the Plato in the basically in the conductivity, Hall conductivity. So that will come because of the, if we put the relativistic electron in the magnetic field, the Landau level is generated, and that is giving me all this only the half fraction. If we do a simple, okay, if we do the all the fractional Hall effect like a if any general fractional Hall effect is can happen in many different fractions, and that can be understood. No, the Landau level cannot explain that. For that you need to go to the composite fermion approach, all these things.
I hope, Tanya, this satisfies your query. And if you have further query, you can write down here. Or any other questions from any other participant, any comment, any suggestions? You can unmute yourself and can directly communicate with the speaker.
Yes.
Any comment from anybody, any query?
So I think no question.
Yeah, I think no more question. Okay, now over to you, Shubhendu. And I want to thank Shudipta also.
Yeah, thanks, Shinjini.
So thank you, Dr. Kanungo. Thank you for your lucid and mind-blowing presentation. Your deliberation must help to grow the research interest to the students of basic sciences in the specific field of research. The wonderful question answer and interactive session will help us to develop the knowledge and improve our theoretical and experimental abilities. So now, I am requesting Dr. Patruleka Mukhopadhyay, one of the senior most teacher and IQAC coordinator of our college, to deliver the vote of thanks. Patruleka ji.
Good evening, everyone. Can you hear me?
Yes.
Good
Yes,
evening,
Padma.
everyone. It's my pleasure to be a part of this wonderful event of 36th National Science Day celebration. On behalf of IQAC Victoria Institution College, I am glad to be here to express our vote of thanks. Firstly, I would like to extend my heartfelt gratitude to our learned speaker, Dr. Sudipto Kanungo, Assistant Professor, Department of Physics, IIT Goa. Thank you very much for such an informative speech that certainly enlightened all the participants today. I am thankful to our teacher in charge, Dr. Umar Universion, for her immense support and guidance she has extended to all of us. My sincere thanks are also due to Physics Department of Victoria Institution College for giving an opportunity to spread a message about the significance of scientific application in our daily life. I would be failing in my duty if I did not congratulate to all the members of organizing committee who handled the event throughout. Lastly, but not least, express my gratitude, including our students who made this year's National Science Day celebration memorable for us. Thanks to all. Have a good night.
Now we may request the participants to please switch on their video so that we can take a group photo. For those it's possible, please switch on the video. সুদীপ্ত, উমাদি এবং আমাদের অর্গানাইজারদের যারা আছে আমরা যদি একটু ভিডিওটা অন করি। শুভেন্দুদা, আপনি ছবিটা নিয়ে নিচ্ছেন তো? শুভেন্দুদা, আর ইউ টেকিং দ্য ফটো?
Yes, yes, yes.
Okay. Participants, if possible, please switch on your video. Okay, thank you all. সুদীপ্ত, একটু আমরা কথা বলতে পারি? Okay. Now participants can leave the meeting. পত্র লেখা দিয়ে উমাদি একটু থেকে যান।
আচ্ছা।